And now we will have our last presentation, and then Alex will close the meeting. Our final presenter is Dorman, who's currently on one part the innovations director at Thales Nano and the scientific advisor for TargetEx. And Gyorgy has plenty of experience with working with small biotechs and related companies in Hungary. I worked together with him actually 10 years ago at ChemAxon, and he also worked at one of the first biotechs here in Hungary called Biorex. And he will give us a short presentation on his implementation of our tools in his drug discovery endeavors.
So thank you very much for the opportunity to talk here. So I try to squeeze my presentation. Anyway, we are riding the Shimano. So that is the major introduction. So we are the users. So we apply the ChemAxon softwares, and not particularly me, but Tunde Tömer is in the audience, and she is the driver, and I'm just the coach. So this is just a short introduction. So this is the outline. I will skip because my presentation will actually describe what I'm talking about. This is a typical slide for the virtual screening, so I will skip this again. I think more of the in the audience know this scheme. So why we need rapid selection of target-based libraries? That is the major starting point. First of all, okay, this one. So this is cheap. The second one, there are lots of companies, they don't have synthesis capacity. It's also very important. The third one is random screening, which normally provides very low hit rate, but with focused library screening, we can exceed particularly 1% hit rate in a particular case. So we need a simple, robust technique to perform a similarity-based search, selecting focused libraries from multi-million vendor libraries. This is here. The solution is basically, for a long time, the 2D fingerprints. And we use the 2D fingerprints from the ChemAxon softwares. So the similarity is expressed in the Tanimoto coefficient. We use the regular coefficient, not the optimized, what we just heard before. And the problem is that it's a little bit of size dependent, but it's not the focus of my talk. So there are two spaces what we use in the similarity search. The design input is actually the reference space. So that our target is phosphodiesterase E5 inhibitors, and we found 27 seed structures from the literature which were really worth to put into our reference space. The compounds were rather diverse, but some of them were closely related to each other, but it was a good starting point. So we also used the ChemAxon softwares from the early parts of our work, because when we extracted, okay, sorry about that. Okay. So when we extracted basically the compounds from the literature, we faced certain problems. That's the UPAC, or the alternative chemical names, what they provided. So we had to transform the structure, or the names to structures. The other thing was what is not really available at the moment at the ChemAxon softwares in the Instant JChem, how to cluster basically the reference, the seed compounds. So we had to visually cluster those compounds. And the third one, which is very important, is basically to define the property space, what the reference compounds actually define. And we use the Lipinski and the Veber rules just calculated with the Instant JChem. So these are the design inputs first, the stage one. The second one is the design inputs two. This is the huge chemical space. This is a real chemical space. That means the compounds are existing from vendor libraries, more or less existing. So just we can say that we can buy those compounds for non-exclusive libraries. The huge library is basically the zinc library, which is available from various vendors. But we turn to the top 10 library vendors, that's 5 million compounds, and here is the list what we actually applied in this chemical space. And there were problems. What is really the ChemAxon software provided a very useful help and assistance, because often there are errors in the SD files, and the Instant JChem combined with the standardizer fixed it. Okay, so I think this is the scheme what Mitso showed in the KNIME flowchart. So this is very similar. So we can see here the commercial libraries. It's 5 million compounds from 10 vendors. These are the seed compounds. These are the inputs. This is the similarity search. And then when we got the first stage results, this is an analog library. These are the figures. And we got almost 9,000 compounds. And we had to filter these compounds out because the requirement to buy 100 to 200 compounds, we had to squeeze to a purchasable library. And how to do it? So what we figured out is the property filtering. So we applied the seed compounds property space to filter out the compounds what we can further select. At the moment, diversity selection is not available, which is for us a sort of disadvantage. So what we can do is we can do certain specified substructure search to define or to reduce the numbers, and also visual inspection to get the compounds to be purchased. So this is the typical action flow what biotech companies actually follow. And I think this is a niche market for the ChemAxon, because there are many companies all over the world which rely on basically vendor libraries. So the similarity search strategy, using the regular Tanimoto coefficient, we had to somehow to define a starting point for the similarity search. And this starting point was actually 70% Tanimoto coefficient. And then this is a certain interval, a range, what we applied around the 70%. And what we agreed as a strategy, so we had to start with like 70% similarity checking, and then if we got 50 compounds or compounds between 50 and 100, that was okay. If we got less compounds than 50 or higher than 500, we had to refine the search by reducing or increasing with 5% the similarity level, and we repeated basically the similarity search and then combined the results from the 10 vendor libraries. So this is the typical strategy. Sometimes it can happen that there is a sudden drop or a sudden increase in the similarity between the 5% change. So we had to then a little bit go lower and then a little bit refine by 2% this similarity search strategy. Then the duplications of the similarity search results were removed when we merged the resulting databases into one huge library. So that was basically the strategy, and there are certain issues what we can then to consider. So still we have, I showed 9,000 compounds, it's too much. So we had to reduce the number of the hits. So normally we can buy libraries or small libraries, 100 to 1,000 compounds. That is what screening companies can afford as an early discovery stage. So since we had basically results from the vendor DBs about 2,000 to 10,000 compounds, so we had to figure out certain strategies how to reduce the numbers. That was the one what I mentioned, the reference property space. So we defined the property space of the seed compounds, all the different Lipinski rules and the Veber rules, and then that was one filtering tool or concept. The second one, we had to find that there were certain overrepresented seed compounds, and the virtual hits coming from those seeds can be reduced. So a sort of even representation is more optimal. The third one is applying the optimal distribution of the resulting chemotypes. And at the moment, we had difficulties to define the chemotypes in the resulting set. So, but anyway, sooner or later it will be solved. It's hopefully the optimized version of the libMCS. And finally, simple diversity analysis would be required. So, just some words about the property space. So, in a short and rapid, robust virtual screening strategy, we cannot use pharmacophore fingerprints because it requires more computation, time-consuming. So the features, pharmacophore features, are considered as statistical features. It's basically connected to structure, but not located to the structural elements. But this is what we used. And I just want to show basically this illustration in a couple of slides, but I go through, just jump through them. So this is the H-bond acceptor property space. This is the 80% medium portion of this range, and we applied this basically in the analog set. And we did the same with the We did the same with the H-bond donors. We did the same, the log P, the molecular weight, rotatable bonds, and the topological polar surface area. So basically, all these together worked as a filtering tool. So the results then, as I mentioned in the flow chart, that means 9,000 compounds were reduced to basically 2,000. And so the second, the overrepresented seeds, basically we had to also reduce somehow. So basically it would be optimal. We were thinking about how to devise a searching strategy through the ChemAxon softwares, but at the moment we are still under progress. So how to directly set the resulting hits from the seed compounds. So just some examples, like the Viagra. We can find that in the 9,000 set we had almost 200 analogs, 60% or more similarity. This is another known PDA5 inhibitor, desantafil, even more. So it's probably the structure reflected many different similarity features in the compounds. That's why it showed a very high, provided very high number of compounds. So I'm gonna go through this. And finally, so we tried to somehow to compare the chemotypes coming from the seed compounds and the hit compounds, but it's rather difficult. If you use the present version of the libMCS, so you can see that we cannot find the real chemotypes because the reoccurring structural motifs are just mainly side chains. This is a difficulty, and we really need software which can find the core, the scaffold, and the major substructure. This is similar to the search results. So we should somehow to think about how to solve this problem. And we had some ideas, and I think we discussed with Mitzo and the other guys. So maybe if there will be an option at the structure, what we would like to actually consider as a common substructure or a scaffold or a chemotype, it should have the more bonds around, or at least we can somehow to define how many bonds can be connected to that unit. So this, it requires more consideration, of course, but somehow this could help, and this could lead to a tool which can provide more real core structures, and it would make this flow easier. So just this is the final slide. It's a conclusion and some proposals for. So there are certain specific features what would be nice to combine into a tool for those niche companies which are relying on compound purchasing. So that's what we would propose, of course, and would be nice and would help us a lot. We could benefit from this. So the specific features required, the similarity search. There are certain ideas what I heard that will be incorporated into the new and the 2010 version. Basically, the multiple compound search would be very useful, since normally there are more seeds than databases. All the seed compounds can be searched in 1 dB while automatically removing the duplications. That would be an idea what would be very beneficial to us. And also possibility to set the minimum number of hits, and I think, as far as I heard today, this is already incorporated in the new version. And or the similarity threshold, so together somehow to put together two parameters, and taking into consideration the seed representation what I mentioned. So maybe an automated seed property space determination and direct application would be also beneficial. And finally, as I mentioned, clustering the results into chemotypes and the diversity selection would be also very valuable. So I think that was, in a nutshell, what we experienced during driving the Shimano. So, and one last slide, you can see Tunde here. She is now actually in the audience, and this is what I showed is majority of her work. And I show Sándor, he is the CEO of TargetEx, and the CSO is Zsolt Lőrinc, and young, talented ladies around. Thank you.
Okay, Gyorgy, thank you very much for your presentation. Are there any questions? Oh yeah, there's one question. Sorry? Where, would you like to show it on the... Yes. Okay, I think so.
The solution? You will show the solution?
Not the full solution, but it's one of the programs that you mentioned that's
Okay. If the audience allow me?
Yes,
Okay.
I'll give you one.
this is also part of the work of the drug discovery group. It's not the screen product that I presented in a nutshell, but it's the clustering tool, and clustering offers now a new method called the sphere exclusion that can be used for diverse subset selection. Actually, that's the industry standard algorithm for a diverse subset selection. So that's a simple web interface. So you don't even need to install this thing. You can use it online. And if you perform this exercise, that in this we cluster just 8,000 compounds, then you can have a quick view of them. There they are. And you can see in a descending order the non-singletons, and these are basically a diverse subset.
Okay.
So you just hit this button, and that's a diverse subset.
Can we import it into SD file? The
Yes, sure.
results?
Yes.
Okay, so okay, thank you.